chapters posted up until Tuesday. The exam will cover pretty much everything we go until next Thursday. We're not going to introduce a whole lot of material on Thursday, but we might talk about like buffers or something just to get that covered before the exam. The exam probably won't have anything on buffers, but it could have maybe a small question on buffers, but everything up until this point, right? So pretty much just all the different types of equilibrium. Hopefully after next week we'll be done with equilibrium, move on to thermodynamics. So last time, the first half, we kind of worked through 2 problems for solubility equilibria and one for complex ion equilibria, right? So those were, does a precipitate form given initial concentrations and the solubility product, right? If you're given both of those things, you can determine if a precipitate forms, because if we have something like AgCrO4, 2 minus solid, and this goes to 2 Ag plus CrO4, 2 minus, right? If we look at the initial concentrations for this, how does that, and if initial concentrations in KSP, that can tell us whether or not the precipitate forms, because it'll tell us what about this reaction if you're given initial concentrations and KSP. What can we use the initial concentrations to find? QSP, right? So these can be used to find QSP. And what do we do with Q? We compare that with KSP. So how do those two compare with each other, right? Is it greater than, equal to? If it's greater than, QSP is greater than, what does that mean? This is our expression for KSP, or solubility product, right? QSP is greater than KSP, what does that mean? Am I here? Yeah, precipitate will form, right? Because it's saying the concentration of these two is too large for the equilibrium value. The reaction needs to shift left in the case, right? So if QSP is greater than KSP, the reaction shifts left because the solubility product, which is the product of the 2 aqueous ions, is too large. So we need to get rid of some of those ions. How do we do that? By causing the precipitate to form. If QSP is less than KSP, what happens? Do we form precipitate? No precipitate formations, right? Because the reaction is going to shift towards the right. So we're going to keep dissolving because this is less than what it needs to be. We create more of these ions here. So we're going to shift right to form more of those ions in solution. So whatever we put in there is going to dissolve until it reaches the threshold value. What's the threshold value? What concentrations are when you switch from undersaturated to oversaturated solution, or unsaturated to oversaturated solution? It's at equilibrium, right? And so it doesn't move when it stays the same when KSP equals QSP. That's when we switch between the two. And so once we reach that special value, then we're at equilibrium. We're not going to shift the reaction at all, any more than that. And so we went over a couple problems with that. I'll probably give you another one to work on in a little bit, just to remind us of what that is, right? So that's where we ended with solubility product, and then we also talked about complex ion formation, right? So that was, instead of solubility, where the solubility products tend to be very small because things tend to not dissolve in water. They might not be that soluble in water. Complex ion formation was the opposite, right? Because the formation constants for complex ions tend to be very, very large, right? So for complex ion formation, we can have something like, let's see, what do we use? We use lead 2 plus aqueous plus 4 I minus aqueous was one of the reactions we looked at, to Hg I4 2 minus aqueous, right? And now we have all three of our products and reactants in what phase? Aqueous, right? So we have to take into account that the formation constant now has all of these. In the expression, so instead of just a product, right, that's why it's called the solubility product, we now have all of these in their expression for equilibrium, right? And so we can set up equilibrium problems of this nature too, and when we did that, there's a specific method we generally use to solve the complex ion. So what was the method? Does anyone remember? Right, what's the first step we did when looking at complex ion formation equilibria? We knew that Kf is much, much, much larger than 1, like on the order of 10 to the 30 sometimes. So if Kf is on the order of 10 to the 30, we favor what at equilibrium? Products, right? We favor the products very, very much, right? So in order to simplify these problems, because if we start off with 0 of the products in this case, then the change is going to be large on the way to equilibrium, right? So we're going to form, plus x or minus x of each of these compounds and plus x of those, plus you. And the expression we'll get, then we can't make any assumptions about x because it's large. This makes this kind of hard to deal with because we have something like to the power of 4 here, right? So we know that polynomial will be hard. So the method that we used to simplify these problems in the justification was we used the bounce back method, right? Where we assumed all of the product form first, right? All product forms, and then we kind of bounce back towards equilibrium, right? We make a small change on our way back to equilibrium, just making a little bit of the products. And when we do things that way, the justification for that is that since we're only making a little bit of the reactants in this case, we only make a little bit of the reactants because what tells us that we're only going to make a little bit of them? Kf is really large, right? That means we're only going to make a little bit. We know that that x is going to be very, very small, that change on the way back to equilibrium. We bounce back to make a tiny amount of reactants. That lets us use small x approximation, which will then make these terms that have anything large to the power 2 a lot simpler, right? Because then we can just get rid of that x term, the change term in this expression. Right, so the trick for this one was called the bounce back method. We assume all the product forms. That sets up our initial concentrations for our ice table, and then we just go through the same steps for the ice table. So you guys did a really good job on the quiz of setting up your ice table. So I think most people are starting to get the hang of that. So that's good. And that's where we did one example with that of using the bounce back method to solve for equilibrium concentrations for the complex ions. Okay. And then we started talking about acids and bases, and we're still kind of working through the different definitions of what an acid, what a base is. And once we get to it, we'll see that we can set up equilibrium expressions for acids and bases as well. And so that'll make it so we can use that language to understand acid and base equilibrium and what does that mean. And so similar to everything else we've done, there's generally going to be some standard method to approach those types of problems, but the principles are the same, understanding equilibrium. All right, so for the acids and bases, we discussed two different definitions last time. One was the Arrhenius definition, and the other one was the Bronsted-Lowry definition. And so what was the Arrhenius definition for an acid? How do we define an acid in those terms?
Uses hydrogen ions.
Yeah, it creates H plus, or we could say it creates H3O plus in solution. Right, so it does one of those, things. Those two are used interchangeably a lot when we're talking about acid and base. H plus or H3O plus. So if you ever see one or the other, that those are identical to each other. And what about a base? How do we define a base? Yeah, it creates hydroxide in solution, right? OH minus in solution, right? That's how we define a base. These are relatively simple definitions because OH minus and H3O plus are going to determine the acidity or the basicity of the solutions, right? And we're going to use equilibrium to understand this. We can start thinking about this because these are just ions that are in solution. These just happen to be ions that make solutions very reactive, but we still can understand this in terms of equilibrium, right? So things like common ion effect, all those things come into play when we're looking at acid and bases. And what about Bronsted-Lowry definition of acids and bases? What was an acid in the Bronsted-Lowry definition?
Donates proton.
Yeah, this is a proton donor, right? So it's a source of hydrogen ions, and a base was, by contrast, what? Proton acceptor. Right, so the base was a proton acceptor. It accepted protons from either amphoteric materials or acids, right? So it's now not just about whether we create H3O plus in solution or OH minus, but the idea of neutralization can be just thought of as donating a proton to either a base or water, right? So this introduced the idea of conjugate pairs. Right? And the conjugate pairs were basically if something donates or accepts protons, what's left over would just be the conjugate inverse to whatever it was. So if an acid donates a proton, what's left over, its anion would be the conjugate base, right? So the conjugate base, and then vice versa, if a base accepts a proton, what's left over after you do that is the conjugate acid, right? So we have these conjugate pairs, and these conjugate pairs allowed for the existence of amphoteric materials or substances. And does anyone remember what amphoteric was? It can be both acid or a base, right? So this can act as both an acid or a base, meaning this can donate a proton or it can accept a proton. So you're going to remember an example of an amphoteric substance? Water, right? So something like water is an amphoteric substance, right? Because sometimes it can donate a proton to become OH minus, and that would be its conjugate base, or it can accept a proton to become H3O plus, and that becomes its conjugate acid, right? So water, for example, and we're going to look at this specific relationship today, and go to OH minus, aqueous plus H3O plus, aqueous, where in this case water is acted as both, one water molecule is acted as base because it's accepted a proton, and the other water molecule is acted as an acid because it's donated a proton. All right, so we're going to go through some more definitions for some of these for some of these acids and bases today. So we're gonna go probably the most still used, or not still used, but the most used definition of an acid or a base. We're gonna talk about Lewis acids and bases, which is not gonna be looking at protons anymore, but instead we're gonna be looking at lone pairs. But before we do that, let's take a second and we'll just use this. Where's my lasso? We can use this, which is the same solubility product on the quiz, and see if we can remind ourselves if we're just given a molar solubility. If we have a molar of 0.002 grams per liter, what is the KSP for this reaction? Alright, so if you're just given the molar solubility here, see if you can find, right, so let's take like 5 minutes or so, see if we can at least set it up. See if you can find the KSP for this reaction, right? And we're gonna need to use a couple different things. Use principles of equilibrium. And we're also gonna need to use the periodic table to convert molar solubility to units of what? In our equilibrium constant, or our solubility product, what are the units that we use to calculate that? Molarity, right? So we use molarity. And we need to think about how is molar solubility related to KSP? Or the molar mass we need to convert. 0.002 grams per liter. We just need to convert grams to moles. So what's the molar mass? And what of the species up there are we calculating the molar mass for? I'll put 1, 2, 3. Which one are we calculating the molar mass for? Which one are we going to use to convert? One, 2, or 3? What do you guys think? So let's think about what the molar solubility actually is. If we have Ag2CrO4 is in equilibrium, this is solid, 2Ag plus CrO4, 2 minus, right? If we were to draw an ice table for this, and we start off with 0 of any of our products in this case, we would get an ice table that looks something like this, right? So what X represents here is the amount of silver chromate that dissolves in solution, right? And the molar solubility is defined as what? Remembers what the molar solubility is defined as. It is going to be X. It's the maximum amount that we can dissolve in solution. The maximum amount is another way of saying the equilibrium amount, right? Because any more than that, the equilibrium shifts, right? So the maximum amount that we can dissolve in a given volume of water is called the molar solubility. That's the equilibrium amount. And if we see, when we put whatever amount of this in solution, this X here represents the amount of solid that goes into the aqueous phase, right? Because we subtract this amount from our initial amount, and that gives us the amount of product that we're gonna have, right? So this is why this is defined as the molar solubility. X is defined as the molar solubility here. And what the ICE table allows us to see is that this value x is related to the equilibrium values of our aqueous ions in solution. Right, so that's how we connect these two things, right? You don't have to do an ICE table for this problem. You can just realize that the molar solubility is equal to x, but setting up the ICE table allows you to see, okay, we need to keep the stoichiometry here, right? Because we have 2 moles of silver, and then we only have 1 mole of chromate here. Right, so that's why we have to go into units of molarity, because the concentrations for our KSP here, right? Our KSP is written in terms of the concentrations of these things. So we need to convert to molarity to then use this. And so which compound are we going to use? Like what is the molar solubility is defined for which one? 1, 2, or 3? When we say we can dissolve this much, what's the maximum that we can dissolve, right? It should be compound 1, right? Because that's what we're actually trying to dissolve in solution. So the molar solubility is given to us in terms of 1, right? We need to use the molar mass of 1. Because that is what we are dissolving. Right, so the molar solubility is given to us for compound 1, in this case, the silver chromate. And then we know that that's related to the concentrations of the other 2, but it's not related to the amount of those that are dissolved in solution, or the amount of those that we can dissolve in solution, because those are already solution phase ions, right? Those are already in the aqueous phase. And so what was the molar mass for silver chromate?
322 grams.
Yeah, we'll just do 322 grams per mole. So units of grams cancel out, and all we're left with is units of moles per liter, which is molarity, right? And so what do you guys get when you plug that in? Does anyone get a value for that? You know, make me plug it into my calculator. 0.002 divided by 1, 2, 3, 4, 5, 6. 6 times 10 to the minus 6.2 times 10 to the 6 minus 2 molarity is what I got when I plugged that in. All right, so this is the molarity of AgCr04, our silver chromate. And the molar mass, Ag2Cr04. And so once we have the molarity, all right, what's the next step after we've made this realization here that, okay, X here just represents the molar solubility. We're trying to solve for the solubility product, right? We're trying to solve for, we want to find KSP. All right, so what do we need an expression for? Yeah, we need an expression for KSP, right? So KSP is equal to what? Ag plus power of 2, Cr04, 2 minus, right? And so what do we plug in for these concentrations here? Ag is going to be 2x squared, right? Because this is our equilibrium concentration of Ag. And then chromate is just gonna be X. And now what we've done on the previous page, we've converted the molar solubility into units of concentration, and the molar solubility is just equal to X in this case. So that means that we're gonna have 4 times 6.2 times 10 to the minus 6 cubed. Right, because all I did is I just carried the square here. 2 squared gives me the 4. X squared times x to the power 1 should be x to the power 3, right? So that's where I got the 3 from. And so when you, see, can I just cube root this? Times 4. And so when you go ahead and calculate this, you get 9 point, I don't know why I made it negative. 9.6 times 10 to the minus 16. So that would give me the solubility product. Right, so the important step here is coming up with an expression in terms of our equilibrium concentrations for KSP, and realizing that the molar solubility is just equal to whatever this change is. It's not immediately obvious, but when we look at our dissolving process, we see that whatever we lose of silver chromate has to be equal to the molar solubility, because that's the maximum amount that we can have in solution, because the rules of equilibrium say that. And so if you looked at this value, would it be is this a very soluble compound? What do you think? If KSP is 10 to the minus 16, do you think that's soluble or insoluble? Insoluble, right? Because this is so small, right? We're saying, okay, we hardly have any of our ions in solution, right? And also we can think, if we can only dissolve 0.002 grams in an entire liter, right? Entire liter is like, half of this. If you can only dissolve a tiny, tiny fraction of that in solution, there's probably not a very soluble compound. Okay, any questions on that? All right, so that's very similar to the one that we had on the quiz. And this type of problem will pretty much always be solved this way. The inverse would be you're given KSP, find the molar solubility of the compound, and that's just going to be solving for X given KSP. Okay. All right, so let's continue with acids and bases then. And so why don't you guys take a second and see if you can identify each of the Bronsted-Lowry acid and base conjugate pairs and label them for this reaction. All right, so for the first equation, what's going to be our acid here? H2SO4. Does anyone remember what that's called? That's going to be sulfuric acid, right? H2SO4. So we'll get from more if you trust me. You guys will get very familiar with acids and bases in the next couple of weeks. And then a water is acting as what in this case, in terms of Bronsted-Lowry? The base. And so hydrogen sulfate, which is what's left over, that's our ion. What is that? It's our conjugate base, right? So this is our conjugate pair, right? So our conjugate base is what's left over after our acid deprotonates, right? Because if this equilibrium is going to shift back the other way, then it's going to act as a base and accept a proton. And then we have the conjugate acid, which would be our hydronium ion, right? And if equilibrium goes back the other way, that's going to act as an acid because it's going to donate a proton. And what about on the bottom here? What do we have? Which one's going to be the acid or which one's going to be the base? What donates its proton? Water, so that's going to be our acid, and then bicarbonate is going to be, not sodium bicarbonate, bicarbonate is going to be our base. And so both of these are actually amphoteric materials. Bicarbonate a lot of times is used for neutralization of solutions, right? You put all that sodium bicarbonate in there, and then that'll neutralize whatever acid or base you have in your reaction mixture. So you guys are probably familiar with that from probably last semester when you did titrations. And so then carbonate is going to be our hydrogen carbonate is going to be our conjugate. That accepted proton, that's going to be our conjugate acid. And then a hydroxide ion is going to be our conjugate base. Right, so right now it might seem, okay, a little trivial to identify conjugate acids and conjugate bases, but once we get to looking at equilibrium concentrations of hydronium or hydroxide, which will be important for determining the pH of the solution, you want to be able to identify this pretty easily, right? And you want to see the movement of protons. Generally, product side is always either going to have hydroxide or hydronium in it, right? So that's something to keep in mind right now. So for the next example, we have a couple conjugate pairs, right? So which one of these is not going to be a conjugate pair for acids and bases? And I'll just, so you guys can hold up your fingers. We have 1 or 2 or 3. Yeah, I see a lot. I see some 2s. Yeah, so why would 2 not be a conjugate pair? The charge doesn't change. That's one thing that indicates to us. The charge probably would change for this, but because here we're not losing a proton at all, right? We're changing the number of oxygens. The oxygens aren't donated or accepted in any definition of acids or bases, right? There's no proton exchange here. So there's no proton exchange, so this would not be considered a conjugate pair, right? We're looking at the movement of protons for acids and bases. In general, even when we're looking at Lewis acids or Lewis bases, we're still looking at protons moving because that's what's going to be creating our hydronium or hydroxide in solution. That's actually what's going to change the pH or the pOH of the solution. Okay. And so now we'll talk about Lewis acids and bases. So this is going to broaden the definition of what an acid or a base can be. And so these are not defined in terms of proton transfer anymore. These are defined in terms of electron or lone pair transfer. What that means is that something can act as a lone pair donor or a lone pair acceptor, right? So here we have ammonia interacting with a hydrogen ion or hydronium. Ammonia, if you were just to guess which one of these is going to act as a base and which one of these is going to act as an acid, right? Hydrogen ion can also be considered H3O plus too, right? Those two are used interchangeably. So if you had to guess which one is going to be a base and which one is going to be an acid. Yeah, we think the ammonia is going to be a base, right? Because when we're working on our qualitative analysis, that's what you're adding to make solutions more alkaline, right? So ammonia is most likely going to be the base, and that's because it has an extra lone pair according to the Lewis definition, and it's going to donate that lone pair, right? So this is going to be a lone pair donor, so a donor of electron density, and the acids are going to be lone pair acceptors. Right, so it's still, the compounds that we think of as acids and bases are going to be acids and bases. It doesn't change any of the ones that we've looked at before from being an acid or a base and converting them to the other. It just expands the definition of what an acid or a base can be. And that's because now instead of just requiring, acid to look at the movement of protons, it can be something that just accepts lone pairs, can be defined as an acid. And so Lewis acid is going to be an electron pair acceptor, and the Lewis base is going to be an electron pair donor. So the lone pair that was on ammonia is what bonds to the proton in the previous case. And so the Lewis model doesn't generally expand what we can consider a base, since the lone pair of an electron, the lone pair that's on the molecule has to bond to something, right? So things that acted as a base before generally had lone pairs in general because they needed that to accept a proton in general, right? So from the Bronsted-Lowry definition, you kind of need the lone pair to be able to interact with the proton, right? So for example, if we have something that's like a negatively charged oxygen, like on hydroxide, right, this looks something like that. This lone pair would then interact with a proton. Those two would interact, and you needed that anyway to interact with the proton in the Bronsted-Lowry definition. But what it does do is it expands the definition of what an acid can be. And that's because that means that acids, by this definition, they don't even really need to have a proton on them, right? So they don't even need to have a proton on them because they can just be some sort of electron deficient species or have some empty orbitals, and now I can accept protons. So the same way when we talked about coordination compound, right, we get to heavy metals, the transition metals and stuff, you start seeing weird behavior in bonding. Those can now start to be considered acids because they accept lone pairs, not just because of the movement of protons, but they're now accepting lone pairs. So a couple common elements would be like boron, aluminum, beryllium, and then highly charged cations, right? So a boron compound, right, it can form 3 bonds. I don't know if you guys remember this from, right, so boron can form a trigonal planar structure, right? And if you counted the octet for this boron, how many electrons are around it? 6, right? Because each bond has 2 electrons. There's 3 bonds, so it only has 6 electrons. Like, wait a second, I thought, the octet rule, I needed to, have 8 electrons to fill my octet. Well, boron is happy like this, and what it does is it keeps an empty p orbital. And that empty p orbital can then accept lone pairs, right? So because we still have the existence of this orbital, doesn't have any electrons filled in it, it can now accept and interact with these lone pairs. And so with insufficient octet molecules, you can then act as Lewis acids now. Another one would be like beryllium, which can form, well, it'll only form 2 bonds, and then it'll have 3 empty p orbitals for beryllium. Right? Bless you. So that's another one you may see. Right, so these can now act as Lewis acids because they have these empty p orbitals that can act as electron pair acceptors. Right, they're electron deficient species is what we call them. And so all these, the borons, the aluminums, all of them can act as Lewis acids because they form these kind of coordination complexes with the Lewis bases. Okay, so these will form an acid-base pair, and a lot of times these will also be complex ions if one of the species is charged, right? So if this aluminum, for example, is charged, when it forms the complexation with the ammonia in this case, it's not going to neutralize any charge because it's not going to be transferring electrons or anything like that. It's just sharing electron density with these atoms. We're not forming bonds in the traditional way. And also we can have positively charged cations, right? So small positively charged cations can act acidic in solution. They form a complex with water. And when they form a complex with water, they become highly charged, and that can actually lead to some ionization of the water molecules around this complex, right? And if we lead to some ionization, all of a sudden now we get some H3O plus in solution, so now you have something that's acting acidic in the solution. So even though this is in terms of lone pair acceptors and donors, in the Lewis acid-base definition, it'll still act as an Arrhenius acid because ultimately it's going to be creating H3O plus in solution, right? And that makes it also a Bronsted-Lowry acid because there's some movement of protons in this. It's just not directly related to the aluminum ion itself, right? It's not donating a proton itself, but its interactions with other things lead to the acidity of the solution changing. And so these have empty d orbitals, right? A lot of the times, these empty d orbitals allow them to complex to different, what we would say are ligands when we talk about complex ion formation, right? They'll form a complex with the ligands, and how that works is the lone pairs on these ligands will interact with the empty d orbitals and make a coordination compound like this, right? So here, that's why we have 6 water molecules coordinated to this aluminum ion, right? Because the d orbitals, we have 1 in each axis, right? So there should be 6 spots for water molecules to exist at. So what this would look like, and again, we'll talk about this at the end of the semester, is we're gonna have, there's the water lone pair, water lone pair, water lone pair, and we have our hydrogens on all of these waters. And what ends up happening is the geometry of this arrangement is what allows for ionization or pulling of protons from one of these water molecules here, right? So because now we're sharing electron density here, maybe we're not holding on to this proton as tightly, another water molecule will come and rip that proton off. Now we've created H3O plus in solution, right? And so does anyone remember what kind of shape this would be? Or does anyone have an idea what kind of shape this would be? One of the shapes from Chem 1A. If you have 6 bonding partners and 0 lone pairs on your central atom, right? This is our central atom. It'd be octahedron. I didn't remember that. We have 6 bonding pairs, right? So we have 3. So that's the origin of you know, using these funky d orbitals for a special type of bonding now. All right, and so Lewis acids can be expanded to now think of positively charged cations as acids and bases. All right, so just to summarize, Lewis acids are electron pair acceptors, Lewis bases, electron pair donors. And those are Lewis acids, you can be positive ions or electron deficient molecules, Lewis bases, negative or lone pair carrying molecules. And now we can think of neutralization as not just a proton being donated to create water, but we can also think of neutralization as a reaction where an electron pair is transferred from one molecule to another, or the electron density is shared with another molecule, right? So we can think of neutralization in a different way as well. And so if you have each of these species here, how would you classify them? As Lewis acids or a Lewis base? So why don't you guys take a second, see if you can classify each of these molecules here. This is the first compound here. All right, beryllium Cl2. If we were to draw that out, it would look something, I put 2 there, something like that, right? How many electrons are around the beryllium in this compound? 4, right? So we have 4 electrons, so does it satisfy an octet? Right, so this is not, there's only 4 electrons around here, so no octet. So we would say that's electron deficient. And so is that gonna make it an acid or a base? It should make it an acid, right? So that's gonna be an acid because it's electron deficient. What about OH minus? All right, what would OH minus look like? It looks like this. How do you think that's going to act as an acid or a base? It should act as a base, right? Because we have 3 different lone pairs on that oxygen that we can use to donate lone pairs, right? So there's 3 lone pairs. That means it'll be a base, right? This is not going to be accepting any lone pairs from any atoms, right? It's already negatively charged. It is not going to want more electron density around it. What about boron trihydroxide? What do you guys think? This probably has a funkier name than that, but what's that going to look like? A boron, OH, that's what our molecule is going to look like, right? We have 3 hydroxides, or 3 OH groups, alcohol groups, that are bonded to the boron. How many electrons are around the boron here? 6 electrons. So does it have a full octet? No octet, because we only have 6 electrons on 8. Right, no octet. So this is electron deficient, which means it's an acid. Bless you. What about cyanide? CN. What's the Lewis structure for cyanide look like? Does anyone know? It's going to be C triple bonded to N minus charge on the carbon here. Not minus charge, but. And so, is this going to act like a Lewis base or Lewis acid, you think? Base, right? We have 2 potential lone pairs right there. 2 lone pairs. That tells us that this is going to be a base potentially, right? We also have a negative charge on this ion. So this is not going to want to take more electron density there, right? So what are we looking for? We're looking to see if something is electron deficient, then it's probably an acid. Or is it a small, highly charged metal cation? Or is it going to be a lone pair donor? Do we see a lot of extra lone pairs on these molecules? Those are indicators it's going to be an acid or a base. All right, any questions on that? So we don't need necessarily Lewis structures for this class, but it would be useful to kind of brush up on them in general, especially how many of you guys are planning to take OChem next semester? Yeah, so it would be useful to brush up on them, especially if you're going to go into OChem. Okay, so those are all our definitions of acids and bases. So how do we determine if an acid or a base is strong? So for acid strength, it's going to be the same for bases. It's related to the strength the same way we define a strong or weak electrolyte. So what did we say a strong electrolyte was? We talked about, remember when we did solubility rules, not solubility rules, but for KSP, if we knew the solubility product for 2 different, solids, right, we could determine which one's going to precipitate first based off of that. And usually that's mixing, or we can determine if precipitate is going to form if we mix 2 strong electrolytes together. Right, does anyone remember how we defined a strong electrolyte? It had to do with the dissociation of the ionic compound, right? So a strong electrolyte dissociated 100%. What does that mean? That means that if we have sodium chloride, we put that in water, it'll go to sodium ions plus chlorine ions. Right, so the ionic compound has broken up into its constituent ions. The strength of an acid or base is identical. Right, so a strong acid is going to dissociate its proton 100% of the time. A strong base is going to dissociate hydroxide ion 100% of the time. So this is going to completely dissociate ions into a solution. Which means that if we have something like HCl, actually I think I do that, I'll go over that on the next slide. So strong acid is going to completely ionize, and a weak acid is only going to partially ionize. And what do you think determines how much of it ionizes? If we think about our example of, let's look at, I don't know, lead chloride, lead 2 chloride. Pb 2 plus aqueous, 2Cl minus aqueous. What determines how much of this is gonna ionize? Or what tells us about how much of this is gonna ionize? Right. Ionize, dissociate, we can use those interchangeably. Right? We're starting from a neutral compound and breaking it up into its 2 ions. So what do you think tells us how much of this we end up with? Or what have we been discussing that tells us how much we end up with this?
Initial concentration of the solid.
The initial concentration, right? If we know how much of the solid, technically how much of the solid we start off with doesn't matter, right? Because it's a solid. The amount of solid doesn't tell us the position of the equilibrium. But we can compare the values of this we have in the solution, right? So if we know the initial concentrations of these, right, that'll allow us to compare it to what? If we know the initial concentrations, what can we calculate and compare to? The equilibrium constant, right? We can calculate Q and compare that to the equilibrium constant. So really what tells us how much of this is gonna ionize or dissociate is the equilibrium constant. And so when we're dealing with weak acids and weak bases, the same idea is gonna apply. The equilibrium constant is gonna tell us how much are we gonna ionize in solution. Now, except we're not talking about lead and chlorine, we'll be talking about whatever our acid is initially and H3O plus in the conjugate base of that acid, right? So we're starting to think about how is this equilibrium related to the acid strength. And so this depends on the reaction, right? We have an equilibrium reaction as listed below. So for hydrochloric acid, since it's a strong acid, that means that we're going to do this reaction 100% of the time. This is like our formation constants, right? Except it's even larger than our formation constants. This happens 100% of the time. Our equilibrium constant is infinity because we're dissociating into H3O plus and Cl minus 100% of the time. Conversely, we could also write H plus aqueous plus Cl minus aqueous when we put HCl in water, right? If we were to just get rid of the water molecule, we can just write this. This is the same thing as what we had before, right? The dissociation. And so why might this be useful? Well, if we think about writing an equilibrium constant for this reaction, what would that equilibrium constant look like? Right, what would we omit from it? What would we omit from the equilibrium, our expression for the equilibrium constant in this reaction? What do we look at when we decide what we put in our expression for our equilibrium constant? Right, so this is the same as any equilibrium constant you've done before. Right? And all of them they follow the same exact principles. It's the states of matter, right? So are there any states of matter here we don't include in the equilibrium constant? Liquid water, right? So because we have liquid, we don't include this in the equilibrium. Alright, so we're not talking about that explicitly just yet, but whenever we're writing an equilibrium constant, you're always thinking, what are the states of matter and what do I include in the expression? And so a strong acid is going to be one that dissociates completely. It's going to have a very infinitely large equilibrium constant because the acid dissociates 100% to give you hydronium in solution or H plus in solution, which are the same thing. Right, and so these are going to be the strong acids, right? So any of the halogenated acids except for hydrogen fluoride or hydrofluoric acid, nitric acid, which you guys are using a lot in lab, perchloric acid, sulfuric acid, those are all going to be considered strong acids. And there's some cases, and we'll talk about this probably on Tuesday, this is going to be a diprotic acid, which means that you have two protons that you can dissociate from this ion. The first ion, right, for this is going to be a very strong acid. So that means that it's going to dissociate its first proton 100% of the time. The second proton, however, is going to be a weak acid, right? It's going to have a Ka value that isn't infinitely large. And so for weak acids, how do we treat them? Well, they don't completely dissociate in solution. And so they're going to have an equilibrium constant that's going to be within some range of values. Usually Ka is going to be called the acid dissociation constant, right? And it's going to be for the reaction of the general form, HA plus H2O. This is going to be aqueous. Let me rewrite this a little neater. HA, aqueous plus H2O. Liquid is going to be H3O plus, aqueous plus A minus, aqueous. HA is going to be our generic acid, which means A minus is going to be, what would we call that?
Base.
The conjugate base, right? This is going to be our conjugate base. And so the Ka values are usually going to be somewhere in between 10 to the minus 30 and 10 to the minus 2, right? So these are going to be the typical values for things that are considered weak acids. And so now the equilibrium isn't always going to shift towards the products, right? We don't have an infinitely large equilibrium constant. We're going to have some ratio of A minus present, H0 plus present, and HA present in solution, right? The amount, the degree to which we're going to shift this equilibrium just depends on the specific value of that equilibrium constant. Right, so when we put acetic acid in a solution of water, it changes the pH, but it's not going to change as much as adding the same equivalent of hydrochloric acid, because we're not going to create 1 mole of H2O plus per 1 mole of hydrofluoric acid that we added to the solution. Right, this is only going to partially dissociate, right, and that dissociation is related to the equilibrium of the acid and its conjugate base, which consequentially also is related to the concentration of H0 plus in solution. And that's how we're going to define the acidity of the solution. And so the degree to which an acid is strong or weak depends on the attraction between the anion of the acid. So that would be the conjugate base. Oops, I meant to just write base here. And the relative attraction of the hydrogen ion to the ions in water, right? So that's kind of what gives us the actual physical justification for what is shifting this equilibrium. Does the water want that proton more, or does the conjugate base want the proton more, right? Because a proton is just something that's floating around in solution that's positively charged. Does A minus or H2O with its lone pairs, right, actually I'll draw the whole molecule. All right, which one of these is more attracted to the proton, right? If this is more attracted to the proton, that means you're not going to dissociate completely in solution, right? Because if this feels like more stronger attraction to this, then I'm not going to actually create hydronium in solution because I'm not releasing my proton. If this is more attractive to the proton, then I'm going to dissociate more of this, right? Because the water would rather create H3O plus than have the acid protonated, right, or the conjugate base protonated. And so when the attraction between H plus and A minus is weak, the acid is strong or stronger, right, because that's just a relative amount. And when the acid between H plus and A minus is strong, the acid is considered weak. Right? If this is strong, or sorry, if this is weak between H plus and A minus, that means it's easier for it to get rid of its proton. If that interaction between these is strong, that means it doesn't want to release its proton. We can't create H3O plus in solution. And so by contrast, we can also think about the reverse reaction as well, right? If the anion has a strong attraction to the proton, and let's say you just dumped a bunch of that anion in solution, which is what you do when you make buffer solutions, then the conjugate base is going to be stronger, right? So the stronger the conjugate base, and the weaker the acid, so the stronger the acid, the weaker the conjugate base, and the stronger the acid, or the weaker the acid, the stronger the conjugate base. Right, and that's because the reverse reaction is going to be something like A minus aqueous plus H3O plus aqueous goes to HA plus water. So in this case, if we're thinking about Bronsted-Lowry, right, definition of acids and bases, what is this acting like? Because this is the reverse reaction here. What is A minus acting like? What is it doing? It's acting as a base, right? Because it's a proton acceptor, right? It's taking a proton from hydronium in this solution. And so if this has a strong affinity for the proton, that means it's going to be much more likely to rip this off with a hydronium ion, which means that it's acting as a strong base. How much it wants to pull that proton is acting as a strong base. So the weaker the acid, the stronger the conjugate base. The stronger the acid, the weaker the conjugate base, right? So we're thinking about the affinity of this ion for a proton. That's ultimately what it boils down to. How strongly attracted is this to H plus in solution? And that you can use to determine the relative strength of the acid, right? That's the physical justification for why it is or is not a strong acid. Ultimately, it all boils down to electrostatics, right? It's positive and negative charges interacting with each other. But what properties of that molecule allow it to be more or less attracted? We'll talk about that towards the end of acids and bases, right? How many oxygens are there? Effects like induction, resonance, all of those can affect the strength of acids and bases. Right, and so some of the weak acids, obviously hydrofluoric acid, acetic acid, which is vinegar, formic acid, carbonic acid, all of those, sulfurous acid, right? So here we notice that it's SO3 instead of SO4. Generally, the more oxygen something has, the more acidic it's going to be. And then phosphoric acid, which is a triprotic acid. And so again, this is going to be related to the equilibrium, right? So this is going to be called the acid ionization constant. But really all this is it's just an equilibrium constant, right? This is just an equilibrium constant, except now we're looking at the ionization reaction of whatever an acid is, right? So it's the same thing as our solubility product, right, where we're ionizing some ionic solid. Here we're just looking at the ionization of an acid in solution. So what would Ka be equal here to? Be equal to here? Is a real earthquake. H3O, and then where does that go, in the numerator or the denominator? Numerator, A minus over HA, right? The nice thing about acids and bases is we're always going to be dealing with 1-to-1 ratios for acids and bases, right? We're never going to have to deal with, things to the power of 5, right? Because for every mole of acid, and even for polyprotic acids, there's a way that we deal with them where we don't have to worry about them dissociating multiple hydrogens, right? So even for polyprotic acids, for every mole of proton that we get rid of on the HA, we make 1 mole of H3O plus and 1 mole of HA minus, or A minus. Right, so this is how we would define the equilibrium constant for our acid ionization process. And so we're going to use this then to understand how strong or weak acids are. And so the typical value ranges, like I said, are usually from 10 to the minus 2. It can go up to 10 to the minus 30 once you start getting to alcohols and things of that nature. Those usually aren't really considered acidic anymore. But for each of these, we know that a proton is dissociating, right? We can go through and identify, okay, what's going to be HA, what's A minus, and we are always going to end up with hydronium on one side of the reaction. Hydronium or H plus, right? So here we have hydrofluoric acid. HA is equal to HF. We have water, which is going to create the hydronium ion, and then F minus is going to be our what? A minus, which is our conjugate base, right? Here we have benzoic acid, which is a little more complicated, right? We're donating the proton from, this is called the carboxylic acid group. We're donating this proton to the water to create hydronium, and then the negatively charged anion that's left over is our conjugate base, right? So that means that if you just had this ion, which would be benzoate, if you just put benzoate into the solution, and we say, okay, this is a relatively weak acid, what do you think that that's going to act like if you just put benzoate into the solution? Alright, if we just put A minus into water, what's that going to act like, you think? It'll then act as a proton acceptor, so it's going to act as a base, right? So this is going to act as and so with all these things we're going to be doing with acids and bases, there's always the perspective of 2 different ways that you can look at this. You can look at things acting as a base, or you can reverse reaction, or so you can look at things acting as an acid, or you can reverse reactions and look at them as acting as a base, right? Because the conjugate base acts as a base for any reaction, which means all these constants we're looking at, pH, pOH, all those things are going to be related to each other. All right, and then we go through some examples of some conjugate acid-base pairs, but we're going to skip ahead to the autoionization of water, right? So we said that water can act as an acid or a base, which means it was what kind of material or substance? Amphoteric, right? So this was amphoteric, which means that it can act as an acid or a base, right? So in this case, on the left-hand side, water is acting as the proton acceptor, so it acts as a base, whereas when it's with ammonia, it acts as the proton donor, so it acts as the acid in each of these cases. Which means that if we have pure water, right, water molecules are just floating around in solution. That means every now and then they'll collide and they'll interact in a way such that one water molecule acts as an acid and one water molecule acts as a base, right? This chemical equation is valid because we have both positive and negative charge, so charge conservation is the same, reaction is balanced on both sides. And so that means that if we were to then look at the equilibrium constant, right? So this is called autoionization because it just happens spontaneously with neutral water, right? Every now and then they collide and they interact in this way, which means that even in neutral water, you're gonna have some concentration of H3O plus and some concentration of OH minus. So at its equilibrium, that means that we can write an equilibrium expression for this, and what would the equilibrium expression for this be equal to?
H3O times OH on top.
Yep, it'll be H3O plus and OH minus. David? This would just be K, right? So Ka was specifically for the acid ionization constant. Sorry, I skipped a lot of slides, but the acid ionization constant for this type of reaction here, where you have Ha plus H2O gives you H3O plus and A minus. Here you could think of it in the same way. We haven't gotten enough to start talking about bases yet, but you wouldn't just have HA. You would have HA and B plus that would be interacting with each other because there's a base equation the same way there's an acid equation. We'll get to that though. But here we're not looking at the acid ionization, the generic form of the acid ionization equation. We're looking at just how water autoionizes. And so this is actually going to be its own K. It's going to have its own specific letter associated with it. So we have KSP, KF. What else do we have? KP, KC. Capital K in general, right? We got the basic K. Why did this go all the way back here? Right, so we're gonna add another one. And this is gonna be KW. Right, so we have W for water, right? So they're not very creative with these subscripts for these equilibrium constants, but this is just the autoionization of water. This is called the water ion product. And so what people have done is that you can measure this value, what this value is going to be at a given temperature, right? And so in pure water, right, if autoionization is happening, what can you say about the relationship between H3O plus and OH minus, right? If, again, this was our reaction, H2O plus H2O, oops, H3O plus, aqueous plus OH minus, aqueous. Right, what can you say about the relationship between those? If this is happening in neutral water, right? We're not adding any acid or base. We just have pure water, right? And scientists, they measure the equilibrium constant here. They measure the concentration of it somehow, maybe by doing a titration or something. That allows them to solve for the equilibrium constant.
Their concentrations are equal to each other?
They should be equal to each other, right? Because for every H3O plus we've created in neutral water, there's no H3O plus there. We've also created OH minus, right? So these two should be equal to each other. OH minus should be equal to H3O plus. Which means if KW was equal to these, we can solve for one of them and they'll be the same as each other. So this is OH minus. We then can say this is equal to, we'll just do OH minus squared. All right, we substitute this in for H3O plus. All I did is I took this relationship, I replaced H3O plus with OH minus, and now I get that KW is equal to OH minus squared. I know this is equal to 1.0 times 10 to the minus 14. OH minus squared. I square root both sides. And this gives me that 1.0 times 10 to the minus 7 molarity is going to be equal to OH minus. So if I have any concentration of OH minus or H3O plus in solution, I can then measure, using the autoionization of water, the concentration then of either H3O plus or OH minus. So this tells me that whenever I have water around, that no matter how much H3O plus or OH minus in solution I need to have a total product between them equal to what? So if we're thinking back to our solubility, Pb2 plus of lead chloride, for example, we see that this reaction kind of looks similar to autoionization of water, right? Because we start with two things that don't affect the equilibrium, and then we end up with two things that do affect the equilibrium, right? And if I had a lot of chlorine in solution, I compensate, right, by reducing the amount of lead, right? Because the product of these two things always has to equal what? In that case, for our solubility. Right, when the system's at equilibrium, the product of the concentrations for those has to equal what? What is Pb2 plus Cl minus squared have to equal at equilibrium? The equilibrium constant, the solubility product, right? So that means that if I already have a bunch of chlorine in solution, then I need to have less lead so that it still equals the equilibrium constant. That's what that means, right? If I have too much lead, then the amount of chlorine has to go down to keep the value the same, the product between those two the same. So what we're saying now is that if we know the concentration of H3O plus, and let's say that's some large value, then that means that to compensate, we need to have less OH minus so that the product of them is always equal to this equilibrium constant. Right, so the presence of H0 plus or OH minus into the solution just means that the other one has to increase or decrease to compensate to reach this ratio. And now we know that if we've just had pure water, right, we can define this now, this concentration, as what? How do you think we'll classify this solution if we have this much OH minus, right? And in this case, it's going to be equal to the amount of H0 plus. Or if you think we have the same amount of H0 plus and OH minus, do you think that's going to be acidic, basic, or neutral? It should be neutral, right? So this gives us a specific value of concentration that allows us to classify a neutral solution, right? So this is going to be how we define a neutral solution when we have an OH minus of 10 to the minus 7. Because at that concentration, the concentration of H0 plus has to be what? The same, right? This has to also be 10 to the minus 7, right? Because that's what we did to, justify this, right? We said these two are equal at this point in pure water, because for every mole of H0 plus, we create 1 mole of hydroxide. So we're saying when those two are equal, that's how we define it as neutral. Question?
So if it's larger than that, it becomes
that's
basic?
it. Yep. So then if we have more OH minus, right? If OH minus goes above, let's say it goes to 10 to the minus 5, then what has to happen to H0 plus? It has to go down to compensate, right? Because we need the product to still equal this value at 25 degrees Celsius, right? Because if we change temperature, things move around. So if we increase OH minus, we have to decrease H0 plus to compensate. And if we increase H0 plus, then we have to decrease OH minus to compensate. So this is why in acids and bases, you can always look at things in terms of the OH concentration or the H3O plus concentration. Because we're looking at the auto ionization of water, this is the equilibrium. And we can say a solution is acidic if we have, a high H2O plus concentration or a low OH minus concentration. Because if this is high, that implies that this is low. This is high, that implies that this is low. Right, so that's why we're using the equilibrium here to give us a relationship now how we're gonna classify these solutions as acidic or basic. And so what Colin just mentioned is, well, if we have a neutral solution, then they're gonna be equal to each other because of this ion water product constant. In an acidic solution, H2O plus is gonna be greater than OH minus. So that's gonna be greater than 10 to the minus 7, and OH minus is gonna be smaller than 10 to the minus 7. In a basic solution, you're gonna have then the opposite trend. And so this is true in neutral water, acidic water, basic water, right? Because the equilibrium in water is always gonna be moving towards this equilibrium value for the product constant. And so that's the principle of everything else that we're gonna go based off of here. Is unlike before where we had different solids with different solubility products and stuff like that, pHs for a solution, whenever we add acid or base, we're still comparing it now to the ion water product constant of the auto ionization of water, because the solution is mostly water, right? If we think of this concentration, these are very, very small concentrations, right? Compared to the amount of water that's in solution. That's why water doesn't affect the equilibrium at all. It's just these ions that affect the equilibrium. And so we kind of think of it like a seesaw, right? Where this is the neutral point, right here where we have 10 to the minus 7. And when they're equal to each other, that's how we define it as neutral. If we increase the concentration of H3O, then we have to decrease the concentration of OH minus. That means it's acidic. But that means we can look at a low OH minus concentration or a high H3O plus concentration, and both of those things will tell us if the solution is acidic. And then vice versa for basic solutions. And so then you can always, given the concentration of hydroxide or hydronium in solution, solve for what the other is going to be, right? So we can always solve for H3O plus or OH minus given the other using KW. So if you're given H3O plus or OH minus, then you can use KW to then solve for what the other concentration is going to be. Okay. So in this example, it's saying, well, what's the concentration of H0 plus and OH minus in a solution? That's 0.25 molar barium hydroxide, right? And so if you're just given a concentration of something that has, so it's a metal hydroxide like this, that usually tells you that this is going to be a strong base in this case. All right, so the strong base, what does that mean if we have a strong acid or a strong base?
The conjugate would be a weak acid.
It would be, but when we define something as strong, so there's going to be two different ways we kind of define strong.
That already breaks apart.
Yeah, it breaks apart completely. If we just have a strong base, then it always dissociates 100%. If we have a strong weak acid, that just means it's strong relative to other weak acids, right? This definition strong always means complete dissociation. So this is going to be a strong base, which means that if we dissolve this in solution, what should be the ions that we get? Ba2 plus, which isn't going to affect the hydronium concentration at all in solution, plus what? 2OH minus, right? Because we have two hydroxides that are bonded to the barium, we dissociate two hydroxide ions, right? And so if we start off with 0.25 molar barium hydroxide, what should be the concentration of OH minus in solution? Right, we could do an ice table if we want for this. We don't necessarily have to, but we can. Right? We're given what the change is going to be here in this case, because we know that this completes 100%. So we start off with 0.25 molar of this, we lose 0.25. We start off with 0 of this, plus 0.25. How much do we get of the hydroxide in solution? 2 times that, right? Plus 2 times 0.25, so it'd be 0.5. Right, so if we have 0.5 molar, that's our equilibrium concentration of OH minus. Right, because we dissociate 100% of the OH minus ions in solution. This equilibrium does not go the other way, right? So when I drew the double arrows here, that was wrong. This is a one direction equilibrium. So that gives us our concentration of that. And so then how are we going to use this to solve for the hydronium concentration now?
Did you use KW?
Yep, we use KW, right? Because KW is our equilibrium ratio no matter what. So if we have, this is going to be a large amount of hydroxide in solution, we have to compensate because the concentration of hydronium is going to be what? Larger or smaller?
Small.
Small, right? We have a large amount, so this is going to be small. So we use KW, or the alarm's going to go off here shortly, so I'm going to get you guys ready for that. So we have KW is equal to H3O plus, OH minus. This is 0.5 molar H3O plus, and KW is always 1.0 times 10 to the minus 14. So we get H3O plus is equal to 1.0 times 10 to the minus 14 over 0.5. And so this is going to be a very, very small number, right? 10 to the minus 1. I'll plug it in real quick. The alarm should go off in like 2 minutes. 1 times 10 x to the y, 14, negative, enter, divided by 0.5. So I get the concentration of H3O plus is equal to 2 times 10 to the minus 14. Question, dude?
So if you gave us like this on the exam, we're supposed to know what parts are solid and aqueous, right? Or would you give us?
So this one you don't even need to write this equilibrium right now. You could just look at this chemical formula. If I give you something that has hydroxide bonded to it, it's almost always going to be a strong base, right? So you just know that because there's 2 of the hydroxide ions that you would dissociate into 2 moles of whatever it is that this concentration is. You don't even really have to. This could be aqueous. It doesn't have to be, right? And actually, it doesn't actually make sense for it to be solid because if we're given a concentration, that means it's some solution that we're given. All right, I'm gonna stop it.